All right, we're about to jump into something that sounds like it's straight out of a sci-fi movie, but it's very real and on the horizon. We're talking about holographic MIMO surfaces. This is a technology that's poised to completely change the game for 6G wireless networks. So, let's get right into it.
Seriously, just think about this for a second. What if the very surfaces all around you, the walls, the ceiling, maybe even the windows in your room, what if they could all become these giant, super intelligent antennas? Antennas that could shape and steer wireless signals with absolute precision. That's the future we're diving into today.
So, here's how we're going to break it all down. First, we'll cover what holographic MIMO actually is, then we'll get into the nitty-gritty of how it works. After that, we'll see why it's such a massive step up from what we have now and what it means for the 6G future. And, we'll also look at the big challenges standing in the way.
Okay, first things first. Let's get to the core question. What in the world is holographic MIMO? It's time to turn this futuristic concept into something we can all understand.
So, at its heart, holographic MIMO, or HMIMO for short, is a totally new kind of antenna tech being developed for 6G. Forget the antennas you're used to seeing. I want you to picture a large, smooth surface, almost like a kind of smart wallpaper. And this surface is packed with an insane number of tiny, tiny antenna elements. This whole idea of a nearly continuous surface is the secret sauce here.
And the name holographic is a huge clue. The whole idea is actually inspired by optical holograms. You know how they create these amazing 3D images by perfectly controlling light waves? Well, HMIMO does the exact same thing, but with radio waves. The entire surface works together like one single, super smart brain, processing the signal in space to create the perfect wireless field. It's not just a bunch of antennas, it's a single, cohesive system. Okay, so we've got the what, but what about the how? How does this surface actually manage to control radio waves with that kind of incredible precision? Let's peel back the layers and look at the mechanics.
Well, it really comes down to three key things. First, you've got that dense structure. The antenna elements are squeezed together so tightly, way closer than half a wavelength of the signal. This is what gives it that near-perfect continuous control. Second, you have something called holographic beamforming. This is where the surface intelligently controls the electrical current flowing through it to create these ultra-narrow, almost laser-like beams of energy. And finally, it all comes together in transmission and reception. Those beams are aimed with pinpoint accuracy right at your device, and when a signal comes in, it's captured with an incredible amount of detail.
And here's why that structure is such a big deal. It opens the door to something called near-field communication. See, 6G is expected to use really high frequencies, like terahertz waves, which don't travel very far. HMIMO is tailor-made for these short-range, super high data connections. It's exactly what we need to make those future networks actually work. Now, to really get why HMIMO is such a massive leap forward, you have to compare it to the best thing we have right now in 5G, which is called massive MIMO. And believe me, the differences are, well, they're huge.
Let's just look at this side by side. Today's massive MIMO, it uses separate, distinct antennas. HMIMO, it's that smooth, continuous surface we talked about. Massive MIMO is really built for signals traveling a long way, the far field. HMIMO can handle both near and far, which is a game changer. But the biggest difference, the one that really matters, is resolution. Massive MIMO's spatial resolution is pretty limited. HMIMO's is incredibly high, and that means way, way less interference, or what engineers call side lobes. Think of side lobes as the messy, wasted energy that spills out from a beam. HMIMO cleans all that up, making the signal way more efficient and powerful.
So, we've established that this technology is incredibly precise and powerful. But, so what? What does that actually mean for you and me? Let's talk about the real-world impact this is going to have on the 6G networks of the future. You see, HMIMO isn't just a minor improvement. It's practically a requirement for 6G. It's the key to making those super high terahertz frequencies usable. And once you do that, you unlock mind-boggling data rates. It also makes something called joint communication and sensing possible, where your network isn't just for data, it can also sense what's happening in the physical world. This all lets us create truly smart radio environments and, believe it or not, build networks that are much more energy efficient.
Terabits per second. TBPS. Let that sink in. We talk about gigabit speeds today, right? Well, a terabit is 1,000 gigabits. That's the kind of insane leap in speed we're talking about here. And HMIMO is one of the key technologies that's going to get us there. So what can you do with all that power? Well, the applications are pretty incredible. Imagine walls and ceilings that actively manage your connection to make it perfect. Or localization so precise it can tell where you are down to the centimeter,
which is absolutely critical for autonomous cars and drones. It means we can connect a truly massive number of IoT devices without the network breaking a sweat. And we could finally have perfectly stable, blazing fast internet on high-speed trains. No more dropouts.
But okay, let's bring things back down to earth for a minute. A technology this revolutionary, this powerful, it's not going to be easy. There are some really significant hurdles that researchers need to figure out before this stuff starts showing up everywhere.
And we have to be real here. This is incredibly complex stuff. The hardware is a huge challenge. The amount of computing power you need to process all these signals is just immense. Then there's the question of cost and how to scale this up. And just think about it. You have to control millions, maybe even billions of these tiny elements all at the same time, in real time. That is a monumental task.
So, I want to leave you with this one big question. If any surface, a wall, a desk, a window, can become an active part of our communication network, it changes everything. The question for us is no longer just, how do we build a faster network? The real question becomes, how do we design the intelligent spaces and environments of the future? It's a pretty wild thing to think about.